Hi, I'm Professor Jeff Ackerman from Mechanical Engineering at Colorado School of Mines. I wanted to give a quick tutorial on how to use the new CAM feature in SolidWorks 2018 that we recently got access to create a simple CAM and G code to make this simple part that we can export onto our Haas Mini Mill 2 that we have on campus. So what I like about SolidWorks CAM is it's really neat how it's built right in. So you can take your part, you can design the SolidWorks, edit it, modify it, and all you have to do is click on the SolidWorks CAM feature over here to start working on your CAM file. First thing we got to do is go to define the machine up here in the top left. Under the machine, we're going to pick our 3-axis mill. All the defaults look pretty good for now. I manually changed that max RPM under Tools and Technology Database. You can adjust that, but we're going to adjust the feeds and speeds manually for each tool, just to get a good conservative starting point. Next up, let's go to the tool crib. If you're just starting out for the first time, I'd recommend you may have a lot of tools in here. I would delete all of them and only add the tools that you're going to use in the tool crib, just to keep things simple with our automatic tool changer. To do that, just click on the top up here, shift click to the bottom of your list, and click Remove Tool. All right, so we've deleted our tool crib and we're going to add tools for each operation. All right, next up, under Post Processor, you'll probably default at the top to M3 axis. You're going to want to scroll down to find the Haas VF3, which is the generic Haas post processor that'll work nicely with our Mini Mill 2s in the machine shop. Click Select, and that's going to export the G code that's compatible with the Haas Mini Mill, and that's compatible with pretty much any 3-axis Haas machine. So that looks good. All the other defaults should be just fine for getting started. Let's click OK. All right. Next up, we need to do our coordinate system. So up there, I'm going to delete the coordinate system I had defined earlier. And what I'm going to do is go ahead and select the top left corner of the part. I like to select the top left corner of a part whenever doing CNCing, because typically the CNC fixed jaw, the fixed jaw of the CNC vise, is usually up on the top. That's going to be a fixed anchor point, and it's going to be pretty accurate to zero against when you have your part up there. Whereas this would be the movable jaw, usually on our CNC. So I like to pick the top left corner. All right, so I picked that top left corner. It's hard to see on my computer because the resolution is a little bit wonky in SolidWorks. It looks like Y is going up, Z is going that way, X is going that way. On most CNCs, pretty much all that I'm familiar with, the Z is going up towards the spindle. So what we're going to do is click down here, click this long axis that's pointing up, and that's going to adjust the Z axis. It didn't go in the right direction though. It looks like it's pointing down, in which case we go here, flip the direction, and that looks good. Z is going up. Now for Y is usually going that way, and X is usually going that way, the longest axis of the CNC. But if yours is not quite correct, not in the correct orientation, just go ahead down here, click the Y, click this axis, this line to define the axis. Note how it's going now the incorrect direction. All we have to do is go and flip it right down here, and that looks good. Where Z is going up, Y is going that way, X is going that way. Really important to zero to that point using an edge finder, a digital probe, or even just the paper trick when we're trying to get our Z offset. So just remember that that's our offset or our origin for the part in our CAM. All right, click check. Good to go. Stock manager is the next thing. Now I'm going to assume that we rough cut the aluminum block. Here I'm using 6061 T6 aluminum. This is a pretty common alloy you're going to be using for machining in many different operations. Really easy to cut, and one of my favorite materials. Scrolling down here, this is where we can add offsets, X, Y, Z in each direction. If we have a stock material that's bigger than our final part. So it's often good, if you do have a significantly different size of your stock material versus your final finished part, is to actually measure the stock and plug in those measurements here. Now the only thing you got to be careful of is this defaults to origin. We would just need to change that to FCS, and that's going to update our axis that we just defined. And then we could add, an inch to Z, and we see that we now have a larger stock material in the Z direction if we wanted to, for instance, face all of that down. For now, I'm just going to assume that the part is rough cut, the stock is rough cut to about the size of the part, and this should be good enough for this basic part. All right, go ahead, click check. Now, I already did this earlier, so what I'm going to do is delete this part, the setup that I made, empty the recycling bin. All right, so to get started here, to actually identify these features and start applying some CAM operations, SolidWorks does a pretty good job at extracting machinable features to automatically generate these features from your part. Let's go ahead and see how they do. It's automatically recognizing the features. Let's see how it did. We've got the rectangular pocket 1, that would be this pocket, including this little pin in the middle that we're leaving from the milling operation. We also have this hole group. Those are all through holes all the way down through this part. And that looks pretty good. Those are the main features. And it does a pretty good job at auto-recognizing most features. Okay, next up, we need to actually generate our operation plan here. So initially we're in the CAM feature tree. If we just go over the CAM operation tree right there, now we can actually start defining some operations. So let's start with the pocket. We're going to choose a 2.5 axis mill operation. I like to start with a rough mill. That's just going to rough cut the pocket quickly with as big of a tool as we can get reasonably to fit in there and put on the CNC. So that's a good starting point. We're going to come back in and do a contour mill a little bit later to get a nice surface finish on the outside. Under tool, I'm going to go ahead and add a new tool because I deleted them earlier. Got a flat end mill. I'd like to pick a 1/4 inch end mill for something about this size as a good starting point. So I'm going to scroll down here, look for a 2 flute 1/4 inch carbide end mill. 2 flutes great for aluminum, 4 flutes better as a default for steel. So we're cutting aluminum, so let's pick a 2 flute. Click OK. Awesome, so there's our 1/4 inch flat end mill. You always want to get as big of an end mill for basic roughing operations as you can get and is reasonable for that part. Next up, we're going to go to features. We're going to go ahead and click the feature that was auto extracted. And it's that pocket right there. Let's see how it does. Click check. And it just tried to generate the basic operation for that rough mill. We're going to leave all these defaults. We'll get to them in a second. I'm going to click OK. And note that this is blue, indicating that the toolpath hasn't been generated yet. So we just right click this, click generate toolpath, and we can see the toolpath over here has been generated. So what are we looking at? Those green lines are rapid movements, and the yellow lines are actual cutting operations for the milling. So we see there's about 2 levels of milling here, maybe 3, that little one down there. So let's see how this does. Let's go ahead and simulate right here. Right click that, simulate. What I'm going to do is slow this down just a little bit and then click play. All right, note how the end mill just plunged there on the first cut operation. That can be okay, but we might want to get a slightly more gentle way to enter the pocket operation because that's a pretty healthy plunge. I prefer to use something like a spiral or a ramp, and we'll get to that and how to set that up in 1 second. Now it's coming in, cutting out that outside contour. It's finishing up the last pass. All right. So that's looking pretty good as a starting point. Now we can fine tune that a bit. So we're going to go to rough mill, edit definition. So a couple things we want to check. First thing is we really need to make sure that we have reasonable cutting parameters and feeds and speeds. So I'm going to go down here and click cutting parameters. I'm going to uncheck this box, uncheck this box. Now I have the option to adjust the spindle speed as well as the feed per tooth and the feed rates. It's important not to use the defaults because often SolidWorks tends to overestimate what our machine is capable of, and we'd rather use some more conservative values. So what I recommend doing is going to look up a calculator for feeds and speeds. We're just going to Google Little Machine Shop feeds and speeds. All right, let's take a look. So this is a quick calculator. It gives you a reasonable starting point that you could dial in from here. We're going to choose inch. It's milling, so we're going to leave that. We're dealing with aluminum. I'm going to pick high-speed steel because generally the feeds and speeds are a bit more conservative, and this is mostly the tooling that we have in the shop. Cutting speed 200 looks good. Put in our 0.25 inch end mill. Under RPM, the max speed of our system is 6,000 RPM, And it can't go much beyond that. The default in SolidWorks is 10 or 12,000 RPM, which is way too high for a machine. Now, once we have all those parameters, we're going to go ahead and auto-calculate that chip load, the inches of cut per flute. Okay, so we calculated that. They say we should run our spindle at 3060 RPM. The two cutting edges indicates that 2 flute end mill we're using for aluminum. And they say we should have a chip load of 0.001 inch per flute. That's going to give us all a feed rate of 6 inches per minute, which is fairly slow and a good reasonable starting point. Awesome. Let's go ahead and plug these parameters into SolidWorks CAM. All right, there we go. We're going to plug in 3060 RPM. I'm just going to click on another box and things should update from there. All right. Note how my XY feed rate went down from about 40 to 12.85. As far as feed per tooth, I'm not able to get to 3 decimal places. I would need to go down here and edit the document unit settings to get to 3 decimal places, but I can still enter a number of 3 decimal places of 1 thou or 0.001. Go ahead, click on a box, and there we go. Our XY feed rate has gone down substantially and is much more conservative and a reasonable starting point. Our Z feed rate is still a little bit high. Did not affect that. So what I'd like to do is just lower that to something a bit lower at around 20 inches per minute. All right. To be more conservative, I can slow everything down. I can change my lead in, lead out also to 20. It's just going to slow it down a bit. We could always up those later if we need to speed things up. Great. Those are some good defaults as a starting point. We'll go ahead and click OK. Now at the top, we're going to go to F/S. That looks like the Feeds and Speeds tab. We're going to go up here. Instead of defined by library, which is this library, we have to go in and edit some details. I'm just going to go ahead and pick the tool for my feeds and speeds, which I just defined. Great. Checking that, we've got 3060 RPM. Got some feed rates that we just defined. That's looking good. Go up to roughing. I'll leave all the defaults here. One really important parameter is the allowance. That's going to indicate how much we're leaving on the rough milling operation between the edge of the tool cut and the actual edge of our part. So the default's 10 thou, or is 0.01 inch. I think it's a reasonable starting point. We're going to come in with a contour operation to finish out and cut off this last bit of material, as indicated in this diagram. Cool. All the other defaults seem pretty reasonable. We could adjust the step over, and that's basically the width between the cuts. But that's a reasonable starting point. All right, I could also come over here and change the depth of cut if I want to fine tune these parameters, manually override them with these buttons. I'm just going to leave it as the default, 50%. Okay, under NC, all of these defaults look good. Feature options, we've got a rectangular pocket. This one's pretty important, the entry. So the plunge is a pretty aggressive way to start a pocket operation. What I prefer to use is a ramp or a spiral. Let's try the spiral. Let's click here. Awesome. Now the default spiral should fit in our part. That means instead of plunging straight down, end mills aren't very good at plunging straight down because they have to push a lot of material out of the way, and the cutting edges are on the outside edge of the part or of the tool. So you're plunging, but there's not a lot of place for the chips to go on that initial plunge hole, and it can jam up your end mill or stall the machine in some circumstances. A spiral is a bit better. It's going to actually spiral down into the part, and it's much better operation for getting into an initial milling operation with an end mill. If you're having trouble getting the spiral option to work, you can try the ramp. If you do want to use a spiral, you can edit the radius and pitch. You can make the radius smaller. So we could have the radius and the pitch. And we could get a smaller spiral that would actually fit inside our small pocket. Great. We could probably leave the defaults for now and just see how they do. We're going to leave it at 0.1 inch for both. Awesome. So that's an important parameter to change just so you can get a better lead in to the part. Next up, we've got advanced. All the defaults look good. Posting, we can leave the defaults, and everything else seems pretty reasonable as a starting point. So we're going to go click OK. Note that my new spiral operation just generated, and we can see how the tool is going to spiral down into the part to make those cuts. All right, let's see how we do. Let's go ahead and simulate. Let's watch that initial spiral. There we go. So that's going to enable the end mill to get in there on that pocket and to not plunge, so it's a little bit less aggressive. And it's going to help us start the pocket operation. All right, that's looking good. Next up, we left a little bit of material on the outside of the part. That allowance, let's go ahead and get a contour operation to clean up the edges, the outside. So we're going to go to 2.5 axis mill. Change this from rough mill to a contour mill. We're going to use the same tool, 1/4 inch flat end mill, and we're going to use the same feature. Click check. Awesome. We're going to leave the defaults. Click generate toolpath. And note what that contour is doing. It's already rough cut the pocket. The contour is just going to come to the edges and clean up that last 0.010 of an inch that we left on that rough operation, and do the same on the middle pin here. So it's important to do a rough mill before you do a contour, because we're going to be removing a lot of material with the contour itself. Just give an idea of what we're dealing with. Simulate toolpath. We can watch what the contour is doing. See how it's just tracing the outside edge of the part? And this is why it has to be done after that roughing operation. Great. That looks good. Okay, so if we simulated this whole, both operations, we could right-click Node Part Setup and Simulate, and we'd see that we would get that rough milling operation followed by a contour to get that nice surface finish on the outside edges. Next up, let's go drill these holes. So to do that, we're going to go to Hole Machining Operations. I like to always start off a hole with a center drill or a spot drill. We have a bunch of center drills in the shop, so let's go ahead and use a center drill. This is really important, so we can use a nice stiff drill bit that's able to just make a little divot to start a drill bit and prevents the drill bit from significantly wobbling and making our hole at a slight diagonal. So, pick center drill. We're going to go to the tool. We got to add a new tool for the center drill. Center drill tool type was selected. I usually start with a 1/4 inch, 90-degree center drill. It's a good starting point. Let's go with OK. Got our tool. Let's go to Features. We're going to click on the Hole Group feature. Now we're going to go click Check. Awesome. Leave the defaults. Going to generate toolpath. All right. So it automatically is using the center drill, and we're going to start cutting with that. Let's go ahead and simulate. Let's see what the defaults gave us. Ooh, that's not so good. That is using a center drill to go all the way down to the bottom of the hole. It's not really what a center drill is designed to do. It's really just to create a little divot at the start, just to start the hole. Let's go ahead and fix the depth on that. Center drill, edit definition, go over to tool. You're going to have to change those cutting parameters. It's always a good practice for any tool that you're using. So why don't we do that first? So we got a drill diameter of 0.25. Let's go ahead and look those up. I'm going to click cutting parameters, uncheck that, and I got to put some parameters in here using my little machine shop calculator. Okay, we're going to change this from milling to drilling. We're still dealing with aluminum, high-speed steel drill bit, and we'll leave the default cutting speed. Drill diameter is 0.25, max RPM is 6,000, 2 flutes on our drill bit typically. Go ahead and calculate. That gives us an inch per revolution chip load of 0.007 or 7 thou, and a 27 inch per minute feed rate, which seems pretty reasonable to start with. So let's plug these numbers in. 3820 for RPM, feed per revolution, 0.007. And that changes our Z feed rate to what we calculated on that initial calculator. Click OK. Awesome. Let's go up here to F/S. We're going to change this again from library to tool. And that got brought in our tool feeds the speeds we just defined. Under center drill, spot drilling is the default. and that looks good. The only thing we need to be careful about is we need to set the depths. The dwell means it's going to dwell there for a second, and that's pretty nice just to get a nice contact on our initial divot. NC, we're going to leave all the default planes. Feature options, now we can actually set the depth. So if you see the machining depth, this is all grayed out. All we need to do is click on override machining depth right here. Now we can either manually set a depth that we want, or we can just decide a certain diameter divot we want to create. Now it's a 1/4 inch center drill, so I'm going to select 0.2, which is a little bit less than the drill diameter. I'm going to click set diameter. Note how it just changed the machining depth automatically to 0.1 inch. Seems about right. Awesome. All the other defaults seem reasonable. Let's go ahead and see what that did. Note how our toolpath now comes down just a little bit to create an initial divot. Let's go ahead and simulate that. And then run it. All right, there we go. So we got our center drill to create a bit of a divot right there and there. And that's looking good. Okay. Check. So we got our center drill. Now we actually need to drill the holes. Now I want to do a peck drilling operation so we can bring our drill bit down, in and out, and that's going to help give us a better drilling operation. It's going to help get the chips out of the hole. It's going to enable coolant to flow into the hole as we're machining it. So that's great, especially for long holes. This is a 1 inch stock material through hole. Let's go to hole machining operations. I'm going to change this from center drill to drill. Going to go to tool. Ooh, now I need to actually define the tool that I'm going to be using. I don't actually know that off the top of my head. Let's go ahead and measure that. So I'm going to discard that. Let's go to evaluate, measure. And I believe this was a tap drill for maybe a number 8 or number 10 screw. It looks like we're looking for a diameter of 0.159 inch. So we need that drill bit. All right. So now we can actually find the right tool. Let's go back over to SolidWorks CAM, hole machining operation. Change this from center drill to drill. Now we can select the tool. We've got to add a new one. We're going to change this to drill. And now we're going to look, using this column decimal diameter, we're going to look for 0.159 by scrolling down. Looks like that's it right there. It's a number 21 drill bit. So we're going to click on that, click OK. And there we go. We just added our number 21 drill bit. Go over to features, click on the hole group that we automatically extracted, click OK, leave the defaults. Let's go ahead, right click that, generate toolpath, and let's go ahead and simulate that. All right, so it looks like we're drilling all the way down through. It doesn't show the drill bit pecking, but we'll have to check if it is pecking or not under the tool feature parameters. That's a problem right there. Note that we didn't get our drill bit all the way down through. This is a common default in CAM software. We actually need to add a little bit more drill depth in order to drill all the way down through the parts. It often just drills to the tip. So we can fix that. All right. We're going to edit the operation. Under tool, there's our cutting parameters. Let's do this real quick. You guys know the drill by now, no pun intended. We are going to go over here, change this to 0.159, 6,000 RPM max, 2 cutting edges, assuming it's high-speed steel. Go ahead and calculate. All right, so we got a chip load of just under 5 thou, 0.0048, and RPM should be set to the max of our machine, 6,000. Good starting point. Let's go from there. We're going to change this RPM to 6,000. Feed per revolution, 0.0048. And the Z feed rate should be updated to what we calculated. Great. We're going to go to F/S right there. Change the library to tool. Update our tool parameters right there. Under drill hole parameters, pecking is the default, which is awesome because that's the ideal operation for drilling deep holes in a part. And we could always change our peck depth amount if we were interested. I think the defaults would be pretty reasonable for a 1 inch hole. We could always update these if we'd like. All right, next up, we're going to leave all the default planes. Now here's where we can actually add our tip length. So I kind of check that box, just going to add in the tip length. If I want to make sure it goes all the way down to the bottom of the hole, just to make sure, I can always manually override it right here. And I could say, instead of going 0.03, I could go 1.05 total depth. And that's going to make sure we break all the way down through. Everything else should be good. Click OK. Let's look at our tool path. It looks like we do go down a bit further. And now we can go over here and simulate and make sure that we do in fact make those through holes we're looking for. That's looking good. Awesome, so we're just about done. We got all our operations set up. I'd like to always check the feeds and speeds and also time. So right up here, it's very hard to see on my resolution, but you can check the feeds and speeds, and you can also check the operation total two-path time. This one's going to take 5.42 minutes because that's our rough milling operation. Check our contour. That's looking good. Oh, but it looks like our spindle speed and our feed rate is a bit higher than we'd like. That may be because I need to change the feeds and speeds. Note how this total toolpath time is 0.394 minutes, so it's a much shorter operation than our rough mill that just takes off just a little bit, that those 10 thou of allowance. Let's go ahead and fix the feeds and speeds here. F/S, change the library to the tool, and that should update to the tool parameters we set for our rough mill, because we set that as a tool parameter. All right, and that looks good. Click OK, check the center drill. Those defaults all look pretty good. Quick operation. Click our pecking operation. Feed rates look good. And it's going to take 0.19 minutes, pretty quick. We could reduce the pecking depth, but I think that's a pretty good starting point. We'll just try it. All right, now we've got all our operations. We've checked our feeds and speeds and total time. We can always go ahead and simulate the entire operation. Make sure there's nothing too surprising. Gonna go max out the speed, and let's just take a quick look at what we've created. All right, so that's gonna be our finished part, and it's looking pretty good. Let's go ahead and export this as G-code. Ooh. Yeah, one thing that we could adjust is right there, the center drill operation actually made the hole a bit bigger. And so if we wanted that to just be 0.159 inch hole, we might actually want to go ahead and update that so that we don't have that chamfer at the top. Or maybe that chamfer is good, hard to say. But let's assume that we want, the design intent was to keep this hole of that diameter. We can go to our center drill operation, open that up. And we're just going to adjust the feature options. And I would like to leave it at a 0.15, which is just below 0.159 diameter. Click Set Diameter. That's going to get a slightly smaller machining depth. Click OK. Let's simulate that. Okay, there's a slightly smaller divot. Let's go ahead back here, simulate the whole toolpath, and just make sure everything's cool. All right, there we go. Now we don't have that chamfer because we didn't make that initial center drill hole as large. Great, it's looking good. Let's go ahead and post this as G-code. To do that, we go up here to the top under Post Process. All right, I'm going to change this to a text file. We're going to change it to a standard .nc code format. And I'm going to go ahead and save it in my folder where I have my part. Click Save. Click Play. All right, here's our G-code right down here. It's looking pretty reasonable. Awesome. Let's click OK. Going down to the folder, we can actually see my G-code under CAM Project right there. If I wanted to open it, just right-click it. Can open with. And I'm going to open with Notepad. So you can click on More Apps, click on Notepad, click OK. All right, and there's our G-code. We can go through, if we're more familiar with G-code, we can look up these different numbers online and figure out what these mean. But the big thing I want to make sure is that our feeds and speeds were updated properly. And it looks like a spindles forward command with a speed of 3060, so that's looking pretty good. That's our tool number 1, 1/4 inch carbide end mill. Scroll down here a bit. This is just a bunch of X and Y parameter coordinates. What else? There's a tool number 3, 21 screw mock drill. And that's tool 2, our 1/4 inch 90-degree spot drill. Awesome. Now there are NC code viewers available online where you can actually simulate what this looks like to a generic machine, post-processor machine. But this should work pretty nicely if you load this onto a flash drive and we bring it down to our Super Mini Mill 2 in the machine shop. So that's a quick tutorial of how you can use SolidWorks 28CAM 2018 to make a pretty simple part and just get started. Let me know if you have any questions and look forward to seeing what you guys make. See you next time.